I'd like to thank the organizers, Jean-Marie, Annalisa, and Hans for the nice invitation. Actually, I'm not attending the math physics conference quite often because I don't usually have so much new results. But today I bring something new. The result itself is relatively weak in compare with the other results, but our goal is to propose an alternative approach to handle this problem. By the way, I would like to also to thank Christian Hansel for agreeing change our talks and by the same time give me 10 minutes more. I'm afraid I won't use it in the end, but anyhow. I'm going to talk about a similar topic that you've heard about yesterday given by Tara. It's on the mean field limit and semi-classical limit from many-body Schrödinger equation to Vlasov equation. And this is a joint work with Jinyeop Liew. He just defended last week in KAIST in Korea. He's a PhD student of my previous collaborator, another Lee, Jiong Lee. Matthew is currently doing his PhD in Mannheim. So this is the plan of my talk. Probably I'm going to be relatively fast in the first part because you've heard about almost all the stories about this problem. Second part, I will try to start to introduce our idea how to get directly from the Schrödinger equation to Vlasov equation by using a nice Hosseini measure that we learned from Levin and Solovitz and from this paper a few years ago to rewrite the Schrödinger equation to something like the Vlasov hierarchy. And in the end, I will present also the main idea and the main technical difficulties in the result. Okay, so setting of the problem. As you have seen several times of this equation. Now, not only from this conference, almost all the math physics conferences, which related to many particle equations. So for simplicity, here, we just throw out the external potential. That's usually if the external potential is good enough, there should be no additional difficulties in the analysis. If you talk about the mean field limit. But if it's additional singularity that embedded in, it's another question. It's very difficult, as Tara yesterday already mentioned. And the setting is that we start from this many particle Schrödinger equation with the kinetic operator and this potential operator, which is already written down in the fermionic scale. I put already 1 divided by n in this summation interaction part, and I put also this h squared as the rescaled Planck constant in front of the kinetic operator. And we are studying it also in the antisymmetric wave function space. So we use this L2A is antisymmetric for the n-particle wave functions, which relate to the fermionics case, and the V is the given interaction potential. And it's specifically when we mention that it's in the right scale that we choose H to be n to the power of minus 1/3. So that's the right, should be the, in this setting should be the right scale. And I'm going to also talk about another equation that you heard about, more complicated version 2 days ago concerning the Vlasov equation. I wrote it in this way. We use M just to match the similar notation with Husimi measure. And this is the, if you choose this potential to be Coulomb potential, then this is the Vlasov-Poisson equation. But in our case, so far we cannot handle that singular potentials. And our goal is directly go from this Schrödinger equation to the Vlasov equation, in the sense that, in some sense, that you let the number of the particles goes to infinity. At the same time, of course, the rescaled Planck's constant goes to 0. That's our goal. And I copy one picture from Professor Gold's paper. That's also part of the picture I've seen it yesterday. This half triangle, you've seen it. That the standard structure is you start from an fermionic Schrödinger equation and formally somehow. For the large n, you can approximate it by the Hartree-Fock dynamic. And additionally, that yesterday Charles especially shows her a result in this direction, in the semiclassical regime, from Hartree-Fock to the Vlasov. And the other direction is you can think about first to take the h goes to 0 and then go to this from Liew to the Vlasov equation. Our goal now is to study this diagonal somehow arrow, saying that if we take the right thing, there might be a way to go from n Schrödinger equation to Vlasov equation. And the state of art, I put some names here. Of course, it's far from complete. If your name is not there, forgive me. And you heard about also the history. Somehow in 1980s, there are already some works in this direction for nice potentials. And it's concerning the mean field limit for Schrödinger equation, dynamic time-dependent Schrödinger equation. There are two directions to study somehow. One is the bosonic case, the other is the fermionic case. And I list this bosonic case here by purpose because a few years ago I also did something in this direction. And at that time, I started to learn this topic and started to learn how to compute things by using the notations from quantum field theory, creation, annihilation operators. But I'm not going to talk about bosons today. Concerning the fermionic case, that you see also the list of results that mentioned yesterday, I'm not going to repeat it. It's also include all kinds of possible interaction potentials, including the nice, and also to the potential of Coulomb case is done somehow. Also the nice convergence rate is done. But concerning the semiclassical limit from Hartree-Fock to Vlasov, it's not complete. There are more names here. I just list a little. And for concerning the combined mean field and semiclassical limit, and there was a sequence of works by Gauss and his collaborators by using the so-called Husimi measure, which is the Wigner measure convolution with a Gaussian. And they were able to prove this convergence in the W2, quasi-W2 Wasserstein distance, and has some also a convergence rate. Our purpose is, actually I started to think about this problem. I didn't think about I could do something. It's a very hard classical problem. But now we have something very weak. This talk is just to introduce an alternative approach, not by using the Wigner transform, but directly by using the Husimi measure, the general version of the Husimi measure. Okay, so I switch now to the second part and let you know how it works by using the so-called Husimi measure. Now we start by rewrite the Schrödinger equation into a hierarchy somehow by using this nice coherent state. And I heard this called also PQ coherent state, because in the bosonic case or in the other Hartree-Fock stuff, you have other coherent states. That's the Y operator applied on vacuum. It's not that one, it's this one. And I write it here. Keep you in mind that how it looked like, if in case you're not so familiar with that. But there are many people already know a lot in this direction. F, H is the n to the power minus 1/3. Q, we use Q and P as the space and phase variable, and it is 1 divided by H bar 3/4 F of, now it's a rescaled function, y minus Q divided by square root of H, then with the fixed factor corresponding, I divided by H P dot Y. Okay. In this kind of coherent state, of course, you can define it by any L2 function, which is normalized. And we also copy this notation from that paper that was about, I think, 2015 or 16 on arXiv. And the first time I read it, I find out the structure is very nice, and it's very easy for, at least for those people who don't know so much about quantum mechanics, who can still understand something. Okay, so I will also write this one particle Husimi measure on board. N, I write for k from 1 to n, I just take k equals to 1. Just keep in mind that what does it look like. We use Q1, P1 as the position and the phase factor for the first particle. It is then expectation of any n-fermionic state. A star, well, usually we write dagger, F, H, Q1, P1, and A, the same thing, just write. Means that you use this coherent state to annihilate one particle from this n-particle fermionic state and make it quadratic, square it. Okay, so I copied also one sentence to understand more about what this Husimi measure means. It measures how many particles are in a K semiclassical box with the length scale square root of H. It's very helpful for us to understand it. If you just think about, you take k equals to 1, then it's the measure of the particles. Of course, the particles defined by this wave function, located at the center of Q1, P1 with the length square root of H, this kind of measure. Okay, and how are you going to use this measure? And their work is on a stationary case. Our naive idea was thinking about if I take this psi n as the solution of Schrödinger equation, so what will be the corresponding time derivative or the time evolution of this measure? Then it should look like the Vlasov equation directly. So that we did the computation. In the beginning, when we did the computation, we didn't use the creation annihilation operator kernel, but used the standard computation. It is okay to get the first equation, and it was a big mess for the k equations. Then we switch back to the operator notation. That looks easier. So in the end, after some computations, it's just a matter of computation. Suppose now psi nt, which is the Schrödinger solution of the Schrödinger equation. Then after computation, if I do the time derivative, now this is defined by t. For arbitrary t, it's also t. Of course, the coherent state is not going to be time dependent. So if you do the derivative and plug in the Schrödinger equation, after some computations, you will get, first of all, this transport term, which is very nice, for arbitrary fixed p and q, p1, q1, The first one looks exactly like the second Newton's law, that the derivative of the Q will be P. It's this one. And then later on, for the interaction term, you have the interaction term from the Schrödinger equation. That will give us something look like the two-particle Husimi measure, but not exactly. So actually what we got was this term, this big term. Instead, while this looks like already the two-particle Husimi measure, if you look at the operator kernel, it's something like that, but everything involved by the interaction potential. But we just put our goal there and let the difference to be the remainders. And of course, by the same time, if you compute this one, you get another remainder term, which doesn't harmful. It's not bad because you have some small parameter in front of it. This is the first equation. When we get, for the one-particle Husimi measure, it's related to two-particle Husimi measure, but it's not exactly the BB-GKY hierarchy. You have the remainder terms determined by the Schrödinger solution. It's not totally, so we call it a kind of BB-GKY-like type hierarchy. And what I want to say, and then there is another term there. Of course, then you will see, so the next target would be to find out whether for big N, this guy will, in some sense, converge to a measure. And this guy, well, this is a linear term, and this guy will converge to two-particle some limiting measure, and the remainder terms has to go to 0. And the first term is relatively easy to show is go to 0. The second one is somehow a little bit involved. And since we haven't used the Hartree-Fock approximation, so we still keep the two-particle Husimi measure there. And then what we did is that was continue to do the k-particle Husimi measure to try to compute how it evolved in time. And one could guess that, I pressed the wrong button. Where is it? Yeah. One could guess that it should have the same structure, similar structure that is depend on the k+1 Husimi measure, but with additional error terms. For the k term, you have another one, which is not really interacting with something given here, is for the rest of the particles. Yeah?
Excuse me, sorry to interrupt. Isn't there some combinatorial factor in front of the mk+1 term, like n minus
here.
k over n or something? Yeah. I mean, isn't there some combinatorial factor? That
It was not there. It's included here in a.
Oh, it's included in the definition of the.
In the Husimi measure. You will see that I will list this sequence of properties also later on in the strategy. No, it's not there. Okay, and then you'll see that what's next is very easy. You try to find a compactness argument for all the k-particle Husimi measures and try to estimate all the remaining terms. Okay. This I will skip that I talked about that already, and our main result looks like this. So what we have done is just a compactness argument and error estimate. So the main result, we wrote it like this. It's not directly to Vlasov hierarchy or Vlasov equation. Since we didn't do any further assumption on the initial data. If the initial data is additionally factorized, if the hierarchy has a unique solution, then you go to the Vlasov equation. So our main result looks like this. We need some momentum assumption for the initial data. One particle is enough, because if one particle, this moments for one particle Husimi measure is bounded, then it works for all the arbitrary k thing, because it's symmetric. Another thing, so far what we can do is for the potential, which is very important in the interaction potential. So far we can only handle that the gradient of V is ellipsis. It's the same assumption as Gauss result. And we need another assumption for the L2 function which defined, which is used to define Husimi, coherent state. We needed to have convex support. This should not be a problem, since in the end, it doesn't matter, it goes to delta function. This is just a technical assumption. I'm quite optimistic that we can get rid of this assumption. But we need some momentum boundedness for the F. And the F has to be additionally in H1. The derivative should be, also in L2. It's realizable. And under this condition, we can prove somehow this k-particle Husimi measure is weakly compact in L1, and the weak limit satisfies this infinite hierarchy in the sense of distribution. We can only do it in the sense of distribution, because the error, while the remainder terms estimate, we need arbitrary smooth test functions. You will see it in the strategy of the proof, how it works. As I said, as a result itself, it's not really good. But I want to show the strategy, and we did also the error estimate. Somehow, I think it's ready to write it as a very first version of the result in this direction. Anyhow, the paper, although we didn't write so much in the introduction, it's already 40 pages. So we decided to somehow have it finished now, and we switch to some further topics. Well, not further topics, it's the same topic, but try to have better results later for the future work. And I list it as a corollary here. Also, as I said, if you assume that additionally this initial Hosseini measure can be factorized, approximately factorized, and if you assume that the infinite hierarchy has a unique solution in the sense of distribution, why we wrote it like this, we didn't find appropriate, this must be true, but we have not found it appropriate reference to cite it, and it's not the main target of this work, so we write it like this. Maybe some of you could tell me the infinite, it must be true. Now we have a nice potential. Gradient V is ellipsis. The infinite hierarchy is exactly the infinite Vlasov hierarchy. And then in this case, we can show as a corollary that the Wasserstein, the first Wasserstein distance, goes to somehow in this sense, it goes to 0. Because we have not only the weak compactness, we have also the boundedness of the moments, and it's equivalent that the weak convergence in L1 is equivalent to the convergence in W1 distance. Just a corollary. Further remarks before I show you the main strategy. So the assumptions for initial data, we ask that the initial data has to be symptotically, not symptotic, for big N has to be factorized. And this can be realized by choosing the initial data to be Slater determinant. Also, if you remember, we ask also the initial data should have some this moment, P squared Q1. So the P we need squared, but the Q we just took 1. I will tell you the reason, because I was not so sure whether the Slater determinant will satisfy if I put a square there. It could be sure, it could be true, but I need to check it. So it doesn't matter here. For the 1, I'm already satisfied, because when you do the mean field limit from classical particle system to Vlasov equation, you always use this W1 distance. But the P squared is the corresponding quantum mechanic kinetic energy that must be there. And why I don't put a square is that for the Slater determinant, you need an orthonormal basis in L2. And it's not possible to ask that all of these L2 functions are in H1, at the same time also has L2, this second moment boundedness. But here, it could be true because for the kinetic energy, we have a h bar weight there. But I have to check it. But for the moment, we're satisfied with the first moment in the space variable, in the Q variable. Okay. Another remark is that as the assumption for F, so far we ask you to have convex support, but I think it's just a master thesis somehow to weaken it to be that it has to be in H1 and has to be somehow the square with multiplication of x has to be integrable. Okay, and another remark, furthermore remark, within this framework we haven't used any Hartree-Fock approximation. So if you remember, our result gives you any convergence rate. It's just a convergence. It's just a weak convergence. It's not as good as Chara's result that you have a nice convergence rate. But if we put a Hartree-Fock approximation, somehow to replace the psi n by the Hartree-Fock wave function, then we could hopefully factorize already the two-particle Husimi measure into the multiplication of 2. And then we don't need, on the one hand, we don't need to have this hierarchy. On the other hand, there is a hope to get some convergence rate that is unclear so far. We're going to work on this topic further. And of course, the final goal is whether it's possible to have some similar results for Coulomb potential. That's not so clear. Yeah, then let me go to the proof. A little bit of the proof, not everything, of course. The estimate for the remainder terms are a little bit too lengthy. I will show you the main idea and main difficulties there. Okay, first of all, yes, here. First of all, proposition or lemma, I don't remember. It's again from this paper. That's the basic properties of k-particle Hosseini measure. That's worked for arbitrary antisymmetric wave functions. So it's symmetric in the QP variables, and the integral of it, if you look at the one particle Hosseini measure, the integral is 2 pi cubic. It's always because of here you don't put 2 pi, otherwise you will have it. Now you get the answer. Yeah. Good. Yeah. Right. And the second point is if you do the integral, that gives you this number. It's not always 1. And third one, it has this nice, how do you call it? I forgot. There is a word for this kind of properties. Consistency. Yeah, consistency. But we cannot use that so far. And the last one is almost everywhere bounded. L infinity norm is automatically there. Okay, and if we have a solution of the Schrödinger equation, psi nt, all these properties also hold. Doesn't depend on which kind of wave function. It works for arbitrary. Okay, then we start to do some preparation to estimate the error term, also for the compactness argument. Then we need to somehow not only bound the initial data, also have the bound for the time-dependent version. The first thing, of course, is the number of operator. N, I wrote it directly with the arbitrary k version. If you think about k equals to 1, then the expectation of the number operator is exactly n. and you can get it quite easily. But a remark is that the number operator, expectation of the number operator, is exactly the total mass of Husimi measure multiplied by a constant n. There you can use the nice property of this projection that defined by the coherent state. That's, I'm not going to go line by line. So this tool tells you somehow it's like the conservation of mass for Schrödinger equation. Okay, then we have something more, because for the remainder term, there are not everything nice. If you estimate it in a rough way, you won't get any smallness for the remainder term. So we need something further. That's also we need why we want to have a compact support for the coherent state there. So I wrote again this k-particle version, but you can just think about k equals to 1. It's the same. The number operator is just defined by this somehow. Ax theta, Ax. If you don't cut it off, it will give you expectation n. But we want to cut it off with a character indicator function, which has radius square root of h. It's like the cutoff that mentioned by Benjamin in the so-called fermionic C or whatever. And if you integrate it out by Q, then after the expectation, you will get a square root of n less. I just write this less than square root of n. That's exactly, we wrote it as h. If you think about k equals to 1, then it is the square root of n. One particle cut off the number operator is bounded by square root of n. It's quite natural, because in a number operator, you don't have the frequency variable. You have only the space variable. If you cut only the space, it counts only the square root of the number of the particles in this regime. Okay, the idea, I'm going to skip it, is just a computation. You first integrate out the Q variable, then you get something. And then you use the boundedness of the number operator, you get a square root of n less. This as a preparation for the remainder term, for the estimate for the remainder term. And the other thing is some basic standard fact from harmonic analysis, even a very simple version, that for this kind of, you should also have a name for this, I don't know, fermionic C or whatever, this pure plane wave functions. If you test it by arbitrary test function, it will produce you arbitrary negative power for h. But of course, the constant will depend on the smoothness of the test function, just coming from the integral by parts, in case your x lives outside of the box, if x is not 0. But here we need, this box has a different scale from the square root of h. It has to be bigger, it has to be somehow smaller. The h, square root of h, what's this? Somehow let's just call it, this is h, 1/2. Then we need something less with the length h alpha. Alpha is usually in our older remaining estimates, alpha is between 1/2 and 1. It's a little bit smaller. Okay, this is just as preparation for the remainder term. Okay, then, good. We need something more, kinetic energy, of course. Because so far we just work with the nice potential we didn't do so much effort in getting the kinetic energy. We just computed in a very rough way that suppose the gradient V is bounded, then this direct computation shows, direct computation shows that the kinetic energy at any time will be bounded by the initial kinetic energy plus t squared. And the relation between kinetic energy and the p second moment for the one particle Husimi measure is given here. It just has some error term. It's also written in Levin's paper there. But we need this somehow to get compactness for this sequence of measures, the compactness. And then for the other position moment, okay, we just do it also directly because we have the equation for M1, although it looks quite lengthy, but it has nice structure. If you remember, somehow I will show you again. The equation for one particle Husimi measure looks like this. So if we compute the Q moment, derivative of Q moment for the one particle Husimi measure, then this will disappear. The old things with divergence P1 will disappear, and you will have just these two terms. The main task is to estimate this error term, the R1. It's not a big issue. The R1 has itself an H there. So, here. So the estimate for the Q1 moment can be bounded by just direct computation with extra estimate for the R1. It can be done like this, not so difficult. And then with this, two moment estimate for the P squared and Q with one power, then due to the symmetric property of K particle Husimi measure, we get automatically also the same property, the same boundedness for the K particle Husimi measure, with the increasing in time with T cubic, which is not exponential. We haven't used any ground-Walsh inequality here. Okay, then we are ready to just take the weak limit, because then you can use the Danforth-Pettis theorem to say that it's weakly compact in L1. Then somehow all the linear terms from the equation are done. And then what's remained is to think about how to bound the remainder terms. And basically we have three types of remainder terms. So you can ignore all of these sentences, just focus on these three estimates. For the remainder terms, Rk, which is the divergence in Q in front of it, we can estimate it by square root of h, but not that much, square root 1/2 minus arbitrary small constant. Something, the rate is smaller than 1/2. I just write 1/2 minus. And this will not give any additional difficulty. This has originally a 1 divided by n there. And the other one, the tilde, is the most difficult terms. The tilde comes from the interaction potential thing. And we can fortunately also get the 1/2 minus rate for arbitrary test function. Okay, so far any questions? Good. Then I'm ready. I think I will finish early anyhow. I would take just R1 tilde as one example to show you how we get a remainder terms. How we get an estimate for remainder terms. Okay, the R1 tilde looks like this. We wrote everything out. Just keep the annihilation operator kernel here. It's a lot of things involved, but the P1, Q1 there is the test function. And it's all this UW U, W, Y, V. They are from this creation annihilation operators, the integrals. And somehow this is the M2. This is a two-particle Husimi measure, this gradient V. And that's the one originally computed from the Schrödinger equation, the interaction term. We use the mean value theorem for the function V to write it in this correct term. Okay, now if you count it somehow in a very rough way, this 1 divided by h cubic comes from all of these factors in front of it. It will not do any trouble. But if you think about the difference of V, somehow this will give you a square root of h. This you can see it from the coherent state. This will, somehow this term will give you a square root of h. But then you have two number operators. Especially these two number operators are not both cut it off. Only one is cut it off. Somehow the U and W, they are somehow cut off by this. But the other one, this Y and V, because of the integral also in Q2, they are not cut it off somehow. But just trust me, in the end, if you just estimate it in this way, you will have it as n to a power of 1/3. It's a power of h, 1 divided by h. It's not going to be bounded. So then the trick is now I use part of this term to tell you how the trick is. So here's still not that far. We just, here one step further, we use the delta function for this integral of the P2, then you can replace the V by Y. Then you have somehow the Q2. Q2 replaced, now V replaced by Y. And then Q2, if you do the transformation by using a Q2 tilde, you will have a square root of some remainder term here. This shows you why it produces a square root of h. And if you compare these two terms, this behaves like delta function in the end. W will behave like Q1. The U will also behave like Q1. So this will produce you exactly a square root of h. But in the end, we have to use a triangle inequality to plug in one term and minus one term, plus plug in this term, the gradient of V, Q minus Y. We just plus and minus this term. And again, I use one of that to explain how it works. I just use this term. And now look at this term. It's the same, it's one part of the quantity from last slide. Okay, as I tell you, this will give you a square root of h, but you won't get the nice estimate. The idea is now somehow not cut, but multiply this function by 1. The 1 is written by using the integrator function that W and U, they are already close. If you think about that, our function f has compact support, W and U are already of the scale of square root of h. But that's not enough. We have to have it smaller. So we use W minus U, somehow the distance between these two. Either they are inside of the box or outside of the box. Once they are inside of the box with this length, h with a power alpha, then we don't use the phase factor. We don't use this phase factor. Once it's outside, then we use the phase factor to produce more power for the h. Okay, then as the first part, if you look at the integral, it's only integral in P1 only goes to the phase factor, and the test function. So this will give us h with the power 1 minus alpha multiplied by s. This s has to be balanced later on with the second term. And in the second term, we gain also something. In the second term, originally, you have only w minus v is of order h square root of h somehow, but now we have the h alpha. We gain something. So that's almost the last slide. The first term, we have this 1 minus alpha minus h. Of course, we use the boundedness of number operator and the boundedness of cutoff number operator. One is with n, the other is with square root of n. And in the end, we have some power of h here in the first term, outside of this small domain. And inside of this small domain, we again need the boundedness of number operator cut off the number operator, but there is something more. That what's remained for the integral for this function f is this two thing. And one of the domain is small. Then if we use the Hurder's inequality for this one, and that is smaller than the sixth norm, L6 norm of f, we gain some power also with the measure of the domain. And the L6 is not bad. That's also the reason we need that the function f has to be in H1. It's bounded by the H1 norm. Again, then we gain a 5 factor here, alpha minus 1/2. So if we take alpha equals 1/2, it will not work. So the cutoff has to be a little bit smaller than the semi-classical length. Okay, then in the end, we just balance these two, take them to be the same, then we determine which kind of, how many times of the integral parts for the test function we need. Then in the end, we have a power alpha minus 1/2. If alpha is very close to 1, then we have approaching to the rate of square root of h. But then the price you have to pay is you use a lot of regularity from the test function. So that's the end of my talk, but somehow a small, short summary is, as I said, the goal is just to try to find another idea to reformulate the whole problem. And hopefully we can do something further to have some weaker assumption for the interaction potential, weaker assumption for the function which define the Husimi measure, and of course, if it is possible, to search for some convergence rate in a reasonable distance. Yeah, good. That's the end of my talk. Thank you.